You know, when we think chemistry, we often picture labs, maybe colorful liquids, definitely that huge periodic table.
Right, the classic image.
But if you kind of strip all that away, what's underneath isn't just the science. It feels more like the central science, the one that connects everything. And it really grew out of, well, ancient arts and crafts.
Absolutely. It's foundational. We're not just talking elements here, but the really long, sometimes kind of messy history of humans trying to figure out how stuff worked.
By taking things apart, purifying them.
Yeah, and trying to put them back together in new ways. That's the core of it.
Okay, so that's basically our mission for this deep dive. We're digging into the surprising origins and the big breakthroughs, drawing from our sources a really comprehensive look at chemistry's history and scope.
The goal is to give you the highlights, right?
Hmm.
A journey from, say, ancient perfume makers all the way to, well, modern problems and the chemistry needed to solve them.
Exactly. And that journey, it starts way back, deep in antiquity, thousands of years ago.
It does. Chemistry really began in these early places, Babylon, China, Egypt, modern-day Turkey, as just practical efforts. People needed to separate and purify materials.
Like what sort of things?
Well, think about the techniques that stuck around. Getting metals out of ore, making glass, which is complex, or even figuring out how to produce soap.
Huh. Those are all chemical processes, fundamentally.
Absolutely, and refined over millennia.
What strikes me, though, is that the starting point wasn't some, grand unified theory.
No, not at all.
It was just recognizing that different things in a mixture act differently. Like if you heat something up or filter it, the bits don't all behave the same way.
Precisely. That simple observation is key. And to really anchor this ancient start, our sources point to the world's first documented chemist, Taputi Bolet-Kalam.
Taputi, okay.
Yeah, she was Babylonian, a perfume maker. Her works recorded on cuneiform tablets.
Wow, what was she recording?
Processes. Things like extraction, distillation, filtration, all for making sophisticated perfumes. This is detailed, documented chemical work from, nearly 4,000 years ago.
That's incredible. Really puts things in perspective. Okay, so let's bridge from that kind of artisanal skill, like Taputi's work, to the more systematic study we think of now.
Yeah.
For centuries, especially in the West and Middle East, the focus was alchemy, right?
It was, and we tend to associate alchemy with those really big, maybe mystical goals.
Turning lead into gold.
Right, or finding the elixir of life, that sort of thing.
Yeah.
And look, obviously those specific fantastical goals, they weren't achieved.
Right.
But the rigor the alchemists developed, that was crucial. You asked how they kept that rigor with those fantasy goals. Well, it was the methodology.
How so?
Think about it. If you're spending years trying to turn lead into gold, you have to keep track. Meticulous records of temperatures, times, what solvents you used, weights.
Okay, yeah. It forces a system.
Exactly. It forced this rigorous, systematic experimentation. And that's what ultimately led them to isolate actual elements we know now, like arsenic, phosphorus.
So alchemy failed at its big mission, but it accidentally built the how for chemistry.
Pretty much. The failure to make gold was, in a way, a success for methodology.
That's a great way to put it. I also find the language connection here really interesting. How important were Muslim scholars in, keeping this knowledge going and building on it, especially when things were declining in the Western Roman Empire?
Oh, absolutely critical. They were the ones who kept systematic chemical thinking not just alive, but rapidly advancing between the 7th and 12th centuries.
They weren't just librarians then.
No, they were innovating. And the proof is, in our language today, the terms we still use. Take alcohol.
From Arabic.
Yep, from alcohol, or the distillation device, the alembic, that comes from alembic, which remember was used way back in Mesopotamia, but really perfected during the Islamic Golden Age.
And alkali, too, you mentioned? Yeah.
Yes, alkali, which is fundamental for acid-base chemistry, comes from alkali. It's a clear reminder that chemistry's foundations are truly global, built by scholars who really valued careful observation and documentation.
Okay, let's jump forward then to a real turning point. 16th century, this radical figure, Paracelsus, physician, alchemist.
Right.
And he basically threw out the medical thinking of the time, the whole Galenic, Hippocratic model.
He did. That model had dominated for over 1,000 years, focusing on the 4 humors: blood, phlegm, yellow, and black bile.
So what was his big challenge?
Paracelsus was revolutionary because he said, look, illness isn't always just an imbalance of these humors. He thought diseases had specific external chemical causes.
Oh, so they needed specific chemical treatment.
Exactly. And what's wild is he wasn't just using herbs. He was experimenting with really powerful, even toxic stuff, like mercury.
Mercury? For what?
He used it to treat syphilis and arsenic compounds, too.
Okay, that sounds risky. But our sources say he gave us this one idea, this one quote, that basically underpins modern medicine and toxicology.
He did. It's a cornerstone, really. The dose alone determined that a thing is not a poison.
The dose makes the poison.
Essentially, yeah.
Yeah.
It wasn't about whether something was good or bad inherently. It was all about the amount, the concentration, how it's used.
And that connects to modern ideas.
Directly. It's why we study organ toxicity today. The idea that specific chemicals target specific organs.
Mhm.
It doesn't matter if it's natural or synthetic. It's about the chemical interaction at a certain dose.
That reframed everything. Chemistry at the heart of both healing and harm. Okay, so from defining toxicity, let's shift to defining matter itself. Fast forward again, 17th century, Flemish chemist Jan Baptist van Helmont.
Van Helmont, yeah, another key figure.
He rejected the old ideas too, right? Both the four elements and the alchemical stuff.
He did. He was focused purely on what he could measure and observe. This is a really crucial step in making chemistry more formal, more a science.
And before him, people didn't really distinguish between different air-like things.
Not really. Anything that wasn't solid or liquid and kind of looked like air was just called air or vapor. They didn't have the conceptual tools to tell the difference between, say, steam and carbon dioxide.
So what did Van Helmont figure out?
He was the first to realize that these air-like substances you get from chemical reactions were actually distinct, unique things, completely different compounds.
Not just thinner air.
Exactly. And he realized he needed a word for these invisible, sort of chaotic things that came off reactions.
And he gave us gas.
Precisely. He coined the term gas, and yeah, the thinking is it might come from the Greek word for chaos.
Highlighting their sort of unruly nature.
Kind of. And that simple distinction, giving it a name, making it a category, it was monumental.
How so?
It opened the door for the next wave, people like Boyle, Priestley, Lavoisier, to actually go and isolate, measure, and name all the specific gases. The ones in our atmosphere, the ones from reactions. It basically paved the way for modern atmospheric science.
Wow. From one word to a whole field. Incredible. Okay, let's jump way ahead to today. If someone's trying to get a handle on the field now, what are the main branches? How is modern chemistry sort of divided up?
Yeah, broadly speaking, you can think of modern chemistry in three main interconnected areas. First, maybe the most analytical, is physical chemistry.
Okay.
This is where chemistry really meets physics. It uses a lot of math, quantum mechanics, to understand the why behind chemical reactions.
The underlying principles.
Exactly. And maybe its biggest contribution is the study of thermodynamics.
Right, heat and energy.
Yeah. Think of a chemical reaction like a little factory. Thermodynamics is like the efficiency expert. It tells you three key things. First, stability, will the product actually hold together? Second, feasibility, can this reaction even happen, or does it cost too much energy? And third, speed, how fast can we make it happen? It tells you if a reaction is even possible and how efficient you can make it. That's crucial for pretty much all industrial chemistry.
Makes sense. Efficiency is everything there.
Yeah.
Okay, then the one most people probably picture, organic chemistry. Labs, complex structures.
Yep. Organic chemistry. And it's defined pretty simply. It's the chemistry of carbon-based compounds.
Just carbon.
Well, carbon-based.
Yeah.
What makes this field so huge, I mean, our sources say something like over 90% of all known compounds are organic, is carbon's unique ability.
Which is?
It can form these enormous, complex, stable chains and rings, linking up with hydrogen, oxygen, nitrogen. This network building is why carbon is the basis of life.
DNA, proteins.
Yeah, exactly. DNA, protein, sugars, fats, and also the vast majority of modern drugs. They're all built on these carbon scaffolds.
Okay, so if organic is carbon, what's everything else?
That's inorganic chemistry. Basically the chemistry of everything not primarily based on carbon. So metals, minerals, salts, catalysts.
Non-living world mostly.
Largely, yeah.
Right.
And it drives material science, the semiconductors for computers, special ceramics, what goes on inside batteries. It's the chemistry of, the planet itself and a lot of the infrastructure we build.
Got it. Okay, so with those branches laid out, let's hit the 20th century. Chemistry's impact just explodes globally. We get amazing innovations, antibiotics, plastics, the birth control pill.
Absolutely transformative stuff.
But if you had to pick one chemical innovation that just fundamentally changed human numbers, human demographics, what would our sources point to?
Oh, it has to be the Haber-Bosch process. We really need to talk about this one because its impact is just staggering.
Okay, Haber-Bosch, what did it do?
It figured out how to synthesize ammonia NH3 directly from nitrogen in the air and hydrogen gas using really high heat, high pressure, and an iron catalyst.
And why was making ammonia such a big deal?
Because nitrogen is absolutely essential for plants to grow, but most of the nitrogen in the air, N2, is inert. Plants can't use it directly.
Ah, so Haber-Bosch created usable nitrogen.
Exactly. It allowed for the massive, cheap production of ammonium nitrate fertilizer. Our sources stress this. It's the key invention behind the population boom of the 20th century.
Yeah.
Seriously. It's estimated that without the fertilizer from this process, almost half the people alive today couldn't be fed by current agriculture.
Half the population. That's almost unbelievable. Just staggering. But, okay, that same century also forced us to confront the dark side, the unintended consequences of chemistry on a global scale.
Absolutely. And the list is long, often involving chemicals that were initially seen as miracles.
Like what?
Well, think about leaded gasoline. The neurological damage from long-term exposure to tetraethyl lead, TLL. It was finally banned globally, although our sources note Algeria was the very last country, only in 2021, decades after we knew the harm.
Decades. Wow. And CFCs.
Right, chlorofluorocarbons, great refrigerants, terrible for the ozone layer. That required a huge global effort, the Montreal Protocol, to phase them out.
Which brings us, I guess, to the biggest challenge chemistry is involved in now. Climate change. And what's fascinating is how long we've actually understood the basic chemistry.
Much longer than most people think.
Yeah.
You have to go back to 1856. Eunice Newton Foote, an American scientist.
Look.
Her experiments clearly showed that carbon dioxide traps heat better than regular air. She essentially discovered the greenhouse effect.
But her work was ignored.
Largely, yes, unfortunately. Then later, Svante Arrhenius picked it up.
Right, the Swedish chemist.
In 1896, Arrhenius actually quantified it. He calculated that if you doubled the CO2 in the atmosphere, global temperature would rise by about 5 to 6 degrees Celsius, which is remarkably close to modern estimates.
That's incredible foresight. But the really shocking part is the timing he predicted, isn't it?
That's the kicker. Based on late 19th century industry, Arrhenius figured it would take maybe 3,000 years to double CO2.
3,000 years.
Yeah. But because of the massive exponential growth in industrial activity since then, we're actually on track to hit that level of warming associated with doubled CO2 by the end of this century.
Wow. So chemistry helped figure out the danger, but industry just floored the accelerator.
You could put it that way, yeah.
So looking at the greenhouse gases themselves, beyond CO2, what are the key chemical differences we should know about in terms of, like, potency?
Okay, good question. Water vapor is the most abundant greenhouse gas, naturally, but focusing on the ones from human activity. Methane, CH4, is really important. Chemically, it's different. It doesn't last as long in the atmosphere as CO2. It breaks down faster.
Okay.
But while it's there, it's way more potent. Over, say, a century, it traps about 20 times more heat per molecule than CO2 does.
So a bigger punch, but shorter duration.
Exactly. High impact, short term. Then you've got nitrous oxide, N2O, often from agriculture, fertilizers.
And that one.
Even more potent. Roughly 300 times more powerful than CO2 at trapping heat. And it lasts a lot longer in the atmosphere than methane. Decades, easily.
So understanding those differences lifespan, potency is crucial for tackling climate change.
Absolutely essential. You have to prioritize based on the chemistry, not just lump them all together.
Which brings us to this, I guess, profound irony. Chemistry created a lot of these huge environmental problems.
It did, yeah. Unintentionally, mostly, but yes.
But it's also completely essential to solving them. Developing catalysts to capture carbon, inventing new battery chemistries, even life-saving things like the mRNA and viral vector vaccines for COVID-19, which our sources mention.
Right. Chemistry is language we use to understand the planet's systems, and it's the toolkit we absolutely must use to fix the problems we've created. It's central to survival, to progress.
Well, that really wraps up our deep dive nicely. It's been quite a journey, starting with ancient perfume recipes from Taputi Tekalim.
Right. Recorded on clay tablets.
Moving through those alchemical failures that actually built scientific method and ending up with these huge global challenges of climate chemistry.
It's a vast sweep. And, if we circle back to Paracelsus for a second.
Okay.
He taught us the key difference between a medicine and a poison is the dose, that concept.
Right.
So maybe a final thought for you, the listener, to chew on. When we talk about global issues like greenhouse gases or these persistent pollutants, the dose isn't given to one person. It's spread across the whole planet and across generations.
Yeah.
So how do we need to evolve our understanding of dose, ethically and scientifically, when the recipient is everyone and the effects stretch far into the future? What does safe dose even mean then? That's something to really think about.